Hi all, welcome back to the discussion of the formulation of quantum mechanics. So in the last class, we have discussed two postulates of the Hilbert space formalism of quantum mechanics. So today we can discuss the other three postulates, namely postulate 3, 4, and 5. The postulate 3 would be the most lengthier discussion. The postulate 4 and 5 we can come to finish it very quickly. So we can directly go to our the postulate 3. So we have already discussed the postulate 1 and 2. We can just recall what are those things. The postulate 1. The postulate 1 states corresponding to every system, there is a Hilbert space, and corresponding to the state of the system, we represent is a vector in Hilbert space. So since it is represented as a vector, we can represent we can use the superposition principle always. Okay, that is different from classical mechanics. In classical mechanics, the superposition principle is not always true. It is possible only if the equation of motion is linear. That is, in case of wave, we can use. But in general, it is not possible to use superposition principle in classical mechanics. Whereas in quantum mechanics, we can always use the superposition principle. And the thing is, all the systems or the equation of motions are linear in quantum mechanics. That is why we can represent the state as a vector in Hilbert space, and we can use the superposition principle. And the second postulate is based on measurement. So any measurement or any act of measurement is represented by Hermitian operator, and the result of individual measurement or result or output, better we can use output of individual measurement are the eigenvalues of that Hermitian operator. Okay, so these are the two postulates we have discussed so far, and its implication also we have discussed in detail. So next we are going to the postulate 3. So the postulate 3 states the outcome of measurement of an observable of a quantum mechanical system in a particular state is governed by the expectation value of the corresponding operator in that state. So what is the expectation value? So the expectation value of an operator A, the state psi, is defined as the expectation. This symbol is used for the expectation of operator A. It defined as inner product psi A psi divided by inner product psi psi. Okay, so this definition we will use if psi is not normalized. Okay, so if the state vector is not normalized, that is, if the inner product psi is not equal to 1, then only we'll use this particular definition. So if psi is normalized means if the inner product psi is 1, then there is no need to have this denominator. We can directly we can write the expectation value of an operator is simply the inner product psi a psi. Now this would be the outcome of the measurement. But in the postulate 2, we have said that the outcome or the result of individual measurement are the eigenvalues. But here we say is the outcome of measurement is always the expectation value. Is this contradictory? Then we'll see. Okay, so the postulate 2 actually discuss the outcome of individual measurement, whereas postulate 3 refers the outcome of large number of measurement under identical conditions, or the outcome of measurement on ensemble. Okay, so this postulate 2 and postulate 3 are not contradictory, because the postulate 2 is discussing about the measurement, there is the result of individual measurement on an individual system, on a single system, whereas the postulate 3 is a general thing. It is on the collection of systems. Suppose you have a system of single electron. Now it is not possible to get a single electron in general, isn't it? So if you have a single electron system, then we can only use the postulate 2. But if you have an ensemble of system, then the postulate 3 is valid. So if you have only a single electron, if you measure then spin of that electron, you will get either spin up or spin down. Okay. Now in that single electron, suppose you measure the spin of the electron 100 times. Then sometimes you will get spin up and sometimes you will get spin down. Then we can find out the average value of all those spins. That would be the result of that large number of measurement. So that large number of measurement is going to represent by the expectation value of that operator. So that is the meaning of postulate 3. So the postulate 3, so either, okay, suppose if you have a single electron, okay, so suppose you have a single electron system, you have to measure the spin. Okay, you can measure the spin of the electron using Stern-Gerlach setup. And you're going to measure the spin of electron many times. Okay, so first you measured, you just left it. Secondly, you measured, and third step you measured, the 4 times you measured. So if you're measuring for large number of times, if you measure the spin of electron large number of times, then the result of all those measurements would be the average value of all individual outcomes. So that is what is called the expectation value. So the expectation value of spin is in general psi. Is it psi? So here the state of electron is general. I represent as kid psi. Okay, so now this is a case, or you may have a large number of identical systems. So this is called what is called ensemble. So large number of identical system, and you are going to measure the spin in on all these electron setup. Okay, better we have okay Stern-Gerlach setup. Stern-Gerlach. Okay, so suppose all these electrons are passing through the same setup, the Stern-Gerlach setup, and you will get output. Okay, suppose you have S1, this suppose spin up, you got output. Okay, suppose S1 stands for spin up and S2 stands for spin down. So some will give spin up, some will give spin down, and we can find the average of all the spins, and the average of all the spins will satisfy the expectation value of the operator. So that is what is the meaning of the postulate 3. So again, the postulate 2 is valid. The individual measurement on individual system will give one of the eigenvalue. But if you have the large number of system, the large number of identical system, or if you measure the same measurement in identical way on the same setup for large times, then the result of measurement would be the expectation value, or it would be the average value. So is this making sense to you? The postulate 2 and postulate 3. Okay, again, we'll discuss, we'll continue the discussion of postulate 3, then you will come to know about it. Now, if the state of the system is in one of the eigenvector with eigenvalue ai of the operator A, then the measurement will always give the same eigenvalue, isn't it? Suppose the electron is in spin up, it's already in spin up. So spin up means it is in the one of the eigenvector, it is in the one of the eigenvector of spin operator. Then the action of the spin would always give plus h cross by 2. Okay, so whatever be the number of times you measure, you will get always the same result. So this we have discussed earlier. So if the system is already in one of the eigenstate, then you will get the same eigenvalue always. You will get the eigenvalue corresponding to that eigenvector. Then what would be the expectation value? Expectation value would be the same eigenvalue because you are getting the spin up for 100 times, and what would be the average value? That would be the spin up. So you are getting plus h cross by 2 100 times. Then the average value of the spin would be simply h cross by 2, isn't it? Okay, suppose if your system is in the state vector kit phi I, then the every measurement of a would give the eigenvalue ai, and you will get ai many times. Every measurement you are getting ai. Suppose you measure it for n times, then the average value you have to sum ai n times divided by n, you will get ai. So mathematically, how will you represent the expectation value of operator a is bra phi operator a get phi. Now the operator a acting on get phi would give ai get phi, and since get phi is normalized, I can take this eigenvalue ai outside. We'll have the inner product phi I. So since phi I is normalized, I can simply write as ai. Then the expectation value of the operator would be the eigenvalue of the corresponding eigenvector. So if the system is in the eigenstate, one of the eigenstate of the operator, then you will get the corresponding eigenvalue always. That would be the expectation value. So the expectation in general means it actually refers to a kind of averaging. Okay, so it is the average of all the outcomes. Now, if the state is arbitrary, suppose the state is some ket psi. Now that ket psi we can expand it in terms of the eigenbasis of operator A, because the eigen vectors of operator A would be complete using the completeness property of the basis. Then ket psi we can expand as some over I equal to 1 c I phi a. So that means this ket psi we can write as c1 ket phi 1 plus c2 ket phi 2 plus etc. up to cn ket phi n. Okay, then what would be the result of measurement? So the result of measurement, okay, suppose the ket phi is normalized, so there is a simple thing, otherwise we'll have some denominator. Okay, so if ket psi is normalized, then the expectation value of operator A would be inner bracket psi A psi. Okay, so the expectation value of operator is inner bracket psi A psi. Now the bra psi we can write as the bra phi 1 C1 plus bra phi 2 C2 plus etc. plus bra phi n Cn. Then we have operator A, then C1 ket phi 1 plus C2 ket phi 2 plus etc. up to Cn ket phi n. Okay. Now this operator A acting on phi 1 would give eigenvalue E1. Sorry, eigenvalue A1. And ket phi 1 would give 1. Okay, so we have to assume the basis is orthonormal. So we'll get many inner products here. The inner product between the phi 1 and phi 1, inner product between phi 1 and phi 2, inner product between phi 1 and phi 3, etc. But the inner product between phi 1 and phi 2 would be 0. The inner product between phi 1 and phi 3 would be 0. because it has to satisfy this condition. So if I and j are same, then inner product is 1. If I and j are not same, then inner product would be 0. So the possible inner product I will write here: phi 1 C1 A1 C1 at phi 1. Okay, okay, so there is one small mistake I've done. So there would be complex conjugate on this C1. Because this is your kit psi, then bra psi should have a complex conjugate on these expansion coefficients. So there should be some C1 star here. And this can be plus phi 2 C2 complex conjugate A2 C2 get phi 2 plus etc. Okay, now we can take the C1 star. C1 would be mod C1 square, and we have A1. So this can be taken outside this inner product, and get phi 1, bra phi 1, get phi 1 would be 1. So that would be mod C1 square A1 plus mod C2 square A2 plus etc. Finally, you will have mod Cn square An. All other inner product would be 0. So that is why I have written here the expectation value of operator A would be sum over I equal to 1 to n mod Ci square Ai. So recall this expectation value of operator A is the average value of the observables. Okay, so hence this mod Ci square stands, or it can be interpreted as a probability to get the eigenvalue Ai, isn't it? Okay, so recall if you act operator A on psi, there are different possibilities. We will get A1, we may get A2, up to we may get An. Suppose you get A1 n1 times, you get A2 n2 times, and you get An n times. Okay, so suppose you made the multiple copies of kit psi, and you measured operator A, and we got the eigenvalue A1 n1 times. Suppose 3 times you got the eigenvalue A1, and 4 times you get the eigenvalue A2, and so on. Then what would be the expectation value? The expectation value of operator A would be A1 n1 or n1 A1 plus n2 A2 plus etc. up to nn An divided by the total measurement, which is n1 plus n2 plus etc. up to nn. So we can write this is n1 by n1 plus n2 plus etc. up to nn times A1. So this is a probability to get a chance to get A1 in a single measurement. Okay, the chance divided by the total number of count, that is a probability. So this mod Ci square is nothing but the probability to get the measurement Ai. So our mod C1 square is a probability to get the measurement A1, and mod C2 square is a probability to get the measurement A2, and therefore this can be represented as P of Ai. Okay, so therefore the expectation value of operator A is sum over I equal to 1 to n P of Ai Ci. Okay, so if you have many copies of psi, sometimes you get A1 here, sometimes you get A2, sometimes you get A3, sometimes you get A4. Suppose you made a total of 6 measurement, and 2 times you get A1, 1 times you get A2, and 2 times you get A3, and 1 times you get A4. So, okay, so this is 2 times you get A1 plus 1 time you get A2 plus 2 time you get A3 plus 1 time you get A4 divided by 6. So this would be the expectation value of operator A. So 2 by 6 times A1, 1 by 6 times A2, 2 by 6 times A3, 1 by 6 times A4. So the 2 by 6 is the probability to get A1. So, okay, if you measure 6 times, there is 1 by 3rd probability or 2 by 6 probability to get A1. And there is 1 by 3rd probability to get the measurement A3. And there is 1 by 6 probability for A2 and as well as for A4. So therefore, this mod CA square can be interpreted as a probability. Okay, and we can show that the sum of all this probability must be 1. Okay, so that is can be proved very easily because sum over I equal to 1 to n p of AI is nothing but sum over I equal to 1 to n CI square, and mod CI square is nothing but the inner product psi because the get psi we have written as sum over CI phi I, then bra psi is sum over I, the bra phi I C A star, and what would be the inner product between them would be the sum over I equal to 1 to n mod CA square, and it should be 1. So sum of all probability must be 1. Okay, then what would be the interpretation for CI? Okay, mod CI square is a probability, and therefore CI, which is the inner product phi I psi, is called the probability amplitude for the system to be found in the state phi I. Okay, so remember this get psi we have written as sum over I equal to 1 to n CI get phi I. Now this CI can be written as inner bracket phi I psi. So this inner bracket phi I psi is nothing but CI. It is called the probability amplitude for the system to be found in the state get phi I. And the square of that probability amplitude is a probability that the system to found the system in the state get phi I. Okay, so we can have an example. So consider the ensemble of electron, this state, the C plus plus and C minus minus. That is not required. Okay, so we cannot predict what would be the measurement of what would be the output of the individual measurement, but we can predict the probability. Okay, so even though we cannot predict the outcome of each measurement of spin in the above state, we can find the probability of each outcome. So what is the probability to find the system in spin up? That is simply the square of the probability amplitude. So it would be the mod square of the inner bracket plus get psi, and that would be the mod C plus square. Okay. So similarly, the probability to get spin down, the P of minus, that would be the mod C minus square, and not that mod C plus square and C minus square is 1. Now, if the system is in not normalized, what would be the case? So if get psi is not normalized, if get psi is not normalized, then we can always make it normalized. What we can do is we can define some other state get phi such that it's equal to psi divided by the inner product psi all raised to 1 by 2. Then this phi is normalized. Okay, how will be the what would be the bra phi? The bra phi would be the bra psi, the inner product psi all raised to 1 by 2. Then bra phi get phi would be psi divided by the psi all raised to 1 by 2, the psi all raised to 1 by 2, and that would be 1. So we can always find a normalized vector if your vector is not normalized. So the non-normalized situation is not difficult to handle. We can find the corresponding the normalized vector and find the probability. So this definition, this P plus can be defined in this way if the psi is normalized. If it is not normalized, better normalize it and do the things same. That is, if psi is not normalized, define ket phi, then the probability to find in spin up state is the inner bracket plus phi mod square. That's it. Okay. Now, in the previous example, we have assumed we have discussed about the spin operator in which the eigenvalues are discrete. Now, the operator can have the continuous eigenvalues as well. Okay, suppose the position operator or momentum operator, it can have the continuous eigenvalues. So, consider the position operator. So, let ket x be the eigenvector of position operator corresponding to the position x. Okay, then the probability amplitude of the state vector psi. How will you represent the probability amplitude? The probability amplitude for the psi corresponding to position vector psi. Position vector x, it is the inner bracket x psi, and usually it is represented as psi of x, and it is called the wave function in general. This wave function is also called the probability amplitude for the position psi. Okay, so this is also called probability amplitude, and therefore the probability to find the system in position x would be the mod square of that probability amplitude, or it would be the mod square of psi of x. It's called the probability density, and it is already known to us. There is the wave function is called the probability amplitude, and the mod square of the wave function is called the probability density. And so this interpretation is there in case of the wave mechanics. So our Hilbert space formalism is intact. It is matches with the interpretations of the wave mechanics. There is nothing wrong in the formalism of Hilbert space. So next we can go for the postulate number 4. The quantum mechanical operator corresponding to a dynamical variable is obtained by replacing the classical canonical variable in the later by the corresponding quantum mechanical operators. So this is very lengthy statement, but the thing is very simple. So if you have any classical variable, when you're going to quantum mechanics, just replace that classical variable to a quantum mechanical operator. That's the thing. Okay, so we can have an example. So in classical mechanics, there are many dynamical variables like the Hamiltonian, position, momentum, kinetic energy, etc. Now, when you're going to quantum mechanics, just replace that classical dynamical variable with the corresponding operators. Now, while changing to the operator, you have to think about the commutator problem. And the dynamical, the quantum mechanical operator do not commute in general. So that you have to look it very carefully. That's the only thing when you are going from the classical dynamical variable to the quantum mechanical operators. Okay, so we can continue with an example. So consider a harmonic oscillator problem. So in classical mechanics, the Hamiltonian of a harmonic oscillator, one dimension harmonic oscillator is simply p square by 2m plus half kx square, where m and k are just constant. M is called mass, and k is called the force constant. Now, according to the postulate number 4, I can replace this Hamilton, this dynamical variable with the corresponding operators. So in quantum mechanically, I can write it as h cap is p square by 2m plus half kx square. Now in position basis, I can the momentum is minus ih cross d by dx. So p square would be minus h bar square d square by dx square. So the Hamiltonian operator in position basis the x cap can be simply written as x. So the position basis Hamiltonian can be written as minus h bar square by 2m d square by dx square plus half kx square. Okay, so you should remember about the commutator problem. That is, if you have a classical dynamical variable like c equal to a into b, okay, if you replace this classical dynamical variable to quantum mechanical operator, the thing is the quantum mechanical operator must be ab plus ba all divided by 2. if AB is not equal to BA. If AB is not equal to BA, then the quantum mechanical operator C has to be defined this way. Now this AB plus BA is called the anti-commutator, and we can represent by this symbol. Okay, so this anti-commutator AB is simply AB plus BA. So this has to be checked. Okay, because this is where we'll make some mistakes. So if you are finding, okay, suppose if you define some new operator C equal to x into px or x into p in one dimension, the corresponding quantum mechanical operator is not simply x times p, because x and p do not commute. So the quantum mechanical operator C would be x times p plus p times x divided by 2. This is the quantum mechanical version. So this is classical mechanics, and the corresponding quantum mechanics is this. So that you have to taken care. Okay. Now this postulate, the postulate number 4, is not applicable for certain things like spin, isospin, etc., because there is no classical analog for it. Okay, the spin we cannot represent classically. There is no classical concept for spin, angular momentum. The spin cannot be represented in terms of any dynamical variables, classical dynamical variables in classical mechanics. So there is no the concept of spin in classical physics. So this postulate 4 is not applicable for only such things. But if you have the classical dynamical variable like energy, momentum, position, etc., we can use this postulate 4 to find the corresponding quantum mechanical operator. So this is the spin and isospin are just special cases. So there is no classical analog for it. So our postulate is not applicable for them. Now finally we have the postulate 5. This is the last postulate. So the postulate 5 states that any pair of canonically conjugate operator has to satisfy the following Heisenberg commutation rule. So if you have a canonically conjugate variable like Q and P, then okay, there can be a set of Q's, Q, I, P, I's, where I running from 1 to n. Then all canonically conjugate this coordinates Q, K, Q, L would be 0. Okay, so this coordinate must be commuting, and the momentum, different momentum would also be commuting, and Q, K, P, L would be IH cross delta K, L. Okay, so if you have a coordinate, then the corresponding momenta would not be commuting. So if you have Qx, or it's better we have Qk, Pk, we'll get IH cross. And if you have Qk and PL, you'll get 0 when K not equal to L. So that is the meaning of this expression. So the canonically conjugate variables will have the commutator IH cross. Okay, so if you have suppose x, y, z are the coordinates and the corresponding momenta px, py, pz, the commutator between the x and y would be 0. The commutator between px and py would be 0. But the commutator between x and px would be IH cross, because px is the momentum corresponding to x, and the commutator between x and py would be 0. The x and py commutes. The position along x, the momentum along y can commute. The position along x and momentum along x do not commute. So any pair of generalized coordinate has to satisfy this commutation rule. So that is the postulate number 5, and it usually called the condensation postulate. So this is usually called as postulate of condensation. There is no such thing in quantum mechanics, the postulate of quantization. Okay, so with this, we have completed all the discussion of postulates. So we have 5 postulates in Hilbert space formalism. We have discussed all the 5 and its consequences. And next, we can have the starting of the Hilbert space formalism. We can dig deep into the subject. Now we are ready. So thanks for your complete patience for listening this video lecture. Okay, so we'll have the more fascinating things about quantum mechanics in the coming lectures. So see you everybody. Thanks for watching again. Bye.